Okay, we're finally ready to move on to the first of the deep neural networks, which is the feed-forward neural network. And just a reminder, we did the logistic regression and some of the other traditional algorithms in the prior videos. If you're interested, please do check them out. And you can read more about what I did for each of the traditional algorithms and the logistic regression on my website. And so now we're gonna move forward with the feed-forward neural network. And before I start to talk about neural network, the feed-forward neural network, I just want to mention that in the past, we have tried with different frame duration and with different feature combinations. But based on what I've observed with the prior models I've ran, I decided that with the frame duration of 8 seconds, with the overlap of 4 seconds, have consistently been outperforming any other frame duration. So I will only be working with the frame duration of 8 seconds with the 4-second overlap going forward. Similarly, I have observed that at least for this data set, with the way I process the data, MFCC have been consistently a better predictor than mel spectrogram. So I will also only work with the MFCC as the primary audio feature. So we won't be looking at mel spectrogram for a while I work on the neural network portion. Okay. Yeah, this is not to say that any other duration is no good or mel spectrogram is no good. It's just with this data set and with the way I process the data, it seems like 8 seconds and with the MFCC works a bit better. So that's just what I'm gonna do to kind of improve the efficiency a bit, since each of the neural network is gonna take quite a bit of time to train. Okay, so to move on to the feed-forward neural network, as I mentioned in the logistic regression, feed-forward neural network is very similar to logistic regression, with the only difference being the feed-forward neural network just have hidden layers versus the logistic regression has no hidden layers. This is just the notebook that I used for the logistic regression, and I just renamed it to feed-forward neural network. And we already have the feature, reloading the feature written out in the logistic regression notebook, and have all the other stuff like shuffle the data, one hot encode, stuff like that. So I'm just gonna run the top portion of this notebook. Again, it's the same notebook that we had for logistic regression. The only difference is I will need to change the function for to change it to feed-forward neural network. So I'm going to run this real quick. It's gonna just take a minute, and I'm gonna change this to feed-forward neural network function. And so to create the feed-forward neural network function, I am actually going to use the functional API architecture. It's essentially the functional API architecture essentially is for each layer, the prior layer can be called as if it's a function. So like I can pass in the prior layer, the output from prior layer as an input to the next layer. I will show you in a minute, but so for logistic regression, we use the sequential architecture, but going forward, I will be using the functional API architecture. So to get started, this is gonna be the build model function. And again, we're gonna be adding hidden layers. So I'm just gonna put the comment here real quick. And I want to be able to change the hidden layer size. So I'm actually gonna create another parameter here called hidden layers. And it's gonna be a list. It's gonna be a list where I will pass in the number of neurons for each hidden layers. So here, I'm just gonna pick arbitrarily 128, 64, and 32. So this means I will have 3 layers. The first layer is gonna have 128 neurons, the next 64, the next 32. Okay, so now I'm going to update this function. The first thing I'm going to do is clear back sessions. Again, this is just a good practice, just in case each time when I call this function, it's building on top of the prior prior neural network that I already ran. So I'm going to create a session, and then I'm going to set the input layer. Since we're going to use the functional API architecture, I'm going to specify the layers, and then I'm going to create the model at the end. So the first layer is going to be input. It's going to be the same thing as logistic regression. We're going to use the input features shape 1, which is going to be the number of features to specify the input shape. And the name of the layer is going to be input. Okay. And then I am ready to set the hidden layers. So to set the hidden layers, I am going to loop through this hidden layers parameter. Then hidden layers. And I need to enumerate. Okay, so here I just use the enumerate to enumerate this list. Basically, I is going to be the number, for example, 0, 1, and 2 within the list. And then hidden dim is going to be each of the value within the list. So 128, 64, and 32. And for this, I am going to call it a hidden output. So the hidden output is going to be the output from each of the hidden layer. And each of the hidden layer is going to be a dense layer. So I'm going to use Tensorflow Keras dot layers dot dense. And the units is going to be the hidden dim. Again, the hidden dim is the 128, 64, 32. And then I need to tell it what the activation function is. And for activation, I'm actually going to use ReLU. So there's a couple different activation you can choose. Most commonly for the hidden layers, nowadays a lot of people use ReLU and 10H. For here, I'm going to use ReLU. Essentially, what ReLU does is it squeezes any values between 0 and infinity. So any value that's below 0 is going to become 0, and then any value that's above 0 is going to retain its value. Okay, and then I'm going to put a name here, and the name is not required, but it's just good practice. And I'm going to use a format string so that I can pass in the I into the layer name. So for example, the first pass is going to be hidden 0, and then the second pass is going to be hidden 1, the third pass is going to be hidden 2. Okay, and then I'm going to, since I'm using the functional API architecture, each layer is going to take in the output from the prior layer as the input, right? So here, for example, the first layer output is going to, the first layer is going to take input as the input to produce the hidden output. But since I'm putting this into a loop, I'm going to actually put the input as to get the loop started, I'm going to put input as the hidden output so that I can pass the hidden output here. And then starting from the second layer is going to be, again, passing in the hidden output from the prior layer as the input to the next layer. So on and so forth until we have passed through all 3 hidden layers. I hope this is not too confusing here. And so now my hidden layers are done. I am going to set the output layer. So output layer, again, is going to be, I'm going to change this to be output. The output is going to be a dense layer, and the unit is a 3 because we have 3 labels. And I don't like how this is spaced, so I'm going to just change that. Okay, so my dense layer unit is 3 because we have 3 species. Again, bar swap and EY1. And activation should be softmax because we have more than 2 labels. And the name is going to be output. And this, again, the functional API architecture is going to take in the output from the prior layer, which is the 3rd hidden layer here. The output from the prior layer as input. So I'm passing in the input from passing the output from the prior hidden layer as input. And then this layer is going to create the output layer. Okay. So now I have all the layers specified. I'm going to create the model. So to create the model, I am going to say model equals tf.keras. I think models dot model. And to create the model, I need to specify the input and the output. So the inputs is gonna be my input, which is the input layer, and then my output is gonna be my output layer. And that's it. And then similarly to the logistic regression, we need to compile the model. And for loss, we're gonna use sparse categorical cross entropy, again, because we have 3 classes. And then for optimizer, we're again using Atom, we're passing the learning rate as one of the parameters. And then for metric, we're using accuracy. Okay. I think now this is ready to go. I'm going to run this. And similarly, we're going to visualize the model history by looking at the loss progression and accuracy progression. Okay. As I mentioned earlier, we're only going to use MFCC as the primary audio feature. So I removed anything that didn't use MFCC as the primary audio feature. So here I'm just starting with MFCC and chroma and continent. I create the training features and the validation features. Okay. And then I am ready to fit the model with the training data. So again, remember we changed the build model function. Now we need to, in addition to the input features and learning rate, we also need to pass in the hidden layers. So here I'm just gonna pass in the hidden layers as the default, which is 128, 64, 32 neurons for each layer with 3 layers. And for learning rate, I'm actually gonna reduce the learning rate to 0.01. So since I have more layers, I feel like 0.005 might be too large, which is why I'm reducing the learning rate. But this is something that I will talk about when I do the hyperparameter tuning later. So I'm going to run this. I'm actually going to interrupt there real quick because I want to show you what the output is. So I changed the verbose equal to 1 here so that you can see the progress. All right. So here you can see it's actually training pretty fast since it's just a feed-forward neural network. And let's take a look at the validation accuracy. You can see within each epoch, the validation accuracy continue to increase, which is a very good sign, which means the model is learning. Later, I will show you actually if the learning rate is too large, the validation accuracy actually will not continue to increase because the model will basically overshoot the global minimum because we're using gradient descent as our algorithm here. So while this is training, I'm going to pause the video and I will be back when this training is completed. All right, so this has finished training. It actually was very, very quick. It only took 40 seconds to train. And we can see the learning curve here. And while I had the video on pause, I also went ahead and ran all the other code down below to take a look at the classification report and the confusion matrix. And I also went ahead and ran the model with the other different combinations of audio features. So the first one we did is MFCC and chroma and continent. And then we also did MFCC and RMS and spectral centroid, and then MFCC and chrome, RMS and continents, and MFCC and spectral centroid and continents. So the total the result is at the end here. I'm going to scroll down. And we can see that with MFCC and chroma and continent, the accuracy is already much better than the logistic regression. Remember with MFCC and spectral centroid and continent, this is the best performing one with the logistic regression. Our validation accuracy was only 65%. But here you can see that our validation accuracy has jumped to 75%, which is very good. And I'm just gonna go take a look, stare at the learning curve for a minute, which is the MFCC and chroma and continent. Okay, so from this learning curve, we can see that the epoch I trained it for 100 epoch. Perhaps the model could use another maybe 50 epoch, because we can see the model continues to the loss continue to decrease and accuracy continue to increase, which means the model isn't done training yet. So perhaps I could use another 50 or 100 epoch for the model to actually plateau. And one other thing is, we can still see that there is a bit of overfitting here. The training accuracy is around 10% higher than the validation accuracy. So this is certainly still overfitted, although it is definitely much better than using some of the traditional algorithms like random forest, XGBoost, and support vector machine, where the difference was much larger, like around 30 to 40%. Here, the difference is only 10%. And again, we observe the zigzag in the accuracy and loss progression for the validation data, which suggests that the model is still struggling a bit with the validation data from one epoch to another. The training curve is pretty smooth. I am almost pretty happy with the training curve. Again, we'd probably want to continue training for another 50 epoch or so. And we can also experiment with a different hidden layer size and different number of hidden layers, and also change the learning rate. And also we can look at the different batch size and the training for more epoch. So next, I'm going to do an ablation study by basically changing one parameter at a time to see how the model will perform. And I'm just going to do the ablation study on the best performing feed-forward neural network, which is the MFCC and Chroma and Continent. And I'm going to set up the ablation study offline, and I will be back when the ablation study is ready to be talked about. All right, so I have the ablation study notebook ready, and I already ran it. And just to give you an idea of what this how this notebook was constructed, essentially I copied the notebook that I did for the feed-forward neural network, 8 seconds. And I just added new sections where each section I change one hyperparameter to see how the change impacts the model results. And you can see here we have the default hyperparameter. Again, as a reminder, since the MFCC and Chroma and Continent had the best performance from all the other combinations of feature combinations, I just did the ablation study for this feature combination only. So essentially I changed each hyperparameters, and the first one is I have the default hyperparameter, which is the hidden layer, 3 layers, each with 128, 64, and 32 nodes. And then we'll have the learning rate of 0.0001 with 100 epoch and 32 as the batch size. And then I changed the epoch to 200. And then I also changed the batch size to 8, or batch size to 64. And then I also changed the learning rate to 0.01 and learning rate to 0.0005. And then I also changed the hidden layer size by changing it to 1 layer with 32 nodes, or 2 layers with 64 and 32 nodes, and then 3 layers, but increase the number of nodes for each layer. So I am going to scroll down to look at the results from the ablation study. So here's the result of the ablation study. I just put it into a table format in Markdown so that it's easier to visualize compare the different results side by side. So again, the first one is the default, and this is with the MFCC and Chroma and Continent. And there is a little bit randomness involved. Earlier, we said the training accuracy was 85 and validation accuracy was 75. But here the training accuracy is 84 and validation accuracy is 77. It's not that different. So, again, it's just a little bit randomness involved here. And then with the next one, I increased the number of epoch to 200. And curiously, you can see here, actually the validation accuracy decreased. And if we take a look at the learning curve real quick, we can quickly realize that it's because, at around 100 epoch, the validation accuracy is actually at its best. And then after 100 epoch, even though the model keeps learning from the training data, it actually starts to generalize very poorly with the validation data. So I think at around 100 epoch would be a good stopping point for training. We don't want the model to keep training and it's gonna continue to overfit to the training data and then generalize poorly to the validation data. Okay, and then the next one is I changed the batch size to 8 instead of 32. And we can see that, again, the validation accuracy has decreased. Same with the batch size 64. The validation accuracy also decreased compared to with the batch size 32. And we can, again, take a look at the curve. So with the batch size 8, we can see that it's more overfitted compared to with batch size 32. And with batch size 64, we can see that the model looks like it could continue to train a little bit more. The training and validation looks like it hasn't really plateaued. And then next thing I did is I changed the learning rate to be much bigger than what I originally had and just slightly bigger than originally had. So with increase the learning rate, actually, again, the validation accuracy has decreased compared to our original setting. And just to look at the learning rate when the learning curve when the learning rate is 0.01, we can see that after around 20 epoch, the model has started to greatly perform poorly with the validation data. So this means the model is starting to really memorize the training data and generalize very poorly to the validation data. So we really don't want this. Similarly, for learning rate 0.00005, again, after around, I'd say 20 epoch, the model is starting to perform poorly with the validation data. So, if I were to change the learning rate to be, for example, 0.1 or even larger, I think we're going to see that even with the training data, it's going to overshoot the global minimum here. So again, these are the learning rates of 0.01 and 0.005 are not so great compared to our original setting of 0.0001. Okay, and then the next thing is I changed the hidden layer. So I first tried the hidden layer of one layer with 32 nodes, and the next one is two hidden layer, each with 64 and 32 nodes, and then last is 3 hidden layer, but each with more nodes. And we can see that with only 1 hidden layer and 2 hidden layer, obviously the model is performing poorly comparing to with 3 layers. And then with the 3 layers but more nodes, the model, again, it did not perform as well as our original setting. And I'm just going to take a look at the learning curve real quick. Again, with the 1 layer of 32 nodes, the model is more overfitted, and our training validation accuracy is quite low. So which means the model is not able to pick up all the features and learn all the features and generalize to the validation data very well. So we'd probably want more nodes and more layers. So here, if we add more layers, with 2 layers, the first layer with 64 nodes and second layer with 32 nodes, we can see that the validation accuracy already increased by around 10%. And then for the last one I have more nodes in each of the 3 layers, and we can see again the model is starting to not generalize well to the validation data anymore. The loss is starting to increase, and the accuracy is starting to decrease after around 30 epoch. Which means the model is there are probably too many nodes in the model. So in each layer, the number of nodes are too many, and the model is getting a little too distracted with the so many nodes. Okay, so that's just a very quick view of what the ablation study looks like, and obviously this is not exhaustive. There are still many more things that I could change to see how the model would perform with each change. And but I think that's pretty good for just a feed-forward neural network. Obviously, I would expect the model will perform better with perhaps the CNN and the RNN, which I will talk about next. So for feed-forward neural network, I'm going to just treat this with the default setting with the MFCC and Chroma and Continent as the best performing model for the feed-forward neural network. And that's it for this video. Thank you so much for watching, and I hope I can see you again in the future when I talk about the CNN and RNN.